Okay, let's look at a review topic, uh, average value of a function. And we're going to look at average value of a function, and then we're going to do a couple challenging problems just so you can see the level of difficulty that will be expected of you. Okay, so just as a review of average value, we've got a data table here. And so let's think about this function, and we want to find the average value of this function on the interval between 1 and 4. So just to give us a picture of this, when x is 1, y is 5, 2 it's -1, 3 it's 4, and at 4 it's 8. So that we don't actually know what our function looks like, so we're going to have to approximate the average value. And the way we're going to do that is the idea of a Riemann sum. So between 1 and 2, we could approximate the value using a lower bound. We could approximate that value as being 5 for the whole region. That's our left bound. And then our left bound between 2 and 3, we would say that over that whole region it was -1. And then between 3 and 4, we're going to assume that it's 4, which equals 8. So that's the total area. What we just found is the total area underneath the curve. And if we take this equals the area. And if we take that area and we divide it by our change in x, so 4 minus 1, this equals the average y value. So this idea of dividing the area by the change in x is the average value. So this is saying that on average, over that between x is 1 and x is 4, on average, our y value is something in here. Okay, now that was using a left bound. We also could have used a right bound. So on a right bound, we would have, between 1 and 2, we're choosing our right value. And between 2 and 3, I'm choosing my right value. And between 3 and 4, my right value again. And in this case, my area equals -1 plus 4 plus 8, which is 11. And then I divide the area by the change in x. And this gives me my average approximation for my y value. I use f or y. These are interchangeable. Okay, but that's a very basic idea, not using much calculus. To use calculus, this idea of finding an area is the integral, and this is a review. We've done this before. So if I wanted to find the average value, this value here, we're calling that average value m of f, m for the mean value, so the average. So if I take this mean value and I multiply it by b minus a, so here's my mean value. This is my mean value. Here's my b minus a. And what I do is I get this area. And the idea is that what's significant about this mean value, this average value, is that if I multiplied this average value times b minus a, that's going to be the exact same thing as the actual area underneath my curve throughout that same region. So in essence, what the average value does is it smooths out the curve to being a straight line. So here's an equation that we've looked at before. The only difference is now we're saying big M of f, again, for the mean value of f, and it's this component is just our change in x, and this component here is our total area. Okay, so there's an important theorem, important mean value theorem that we will talk about, and it is as follows. It says that provided that f is continuous on the closed interval a to b, then there exists some number c between a and b such that the area underneath the curve must equal some specific value times b minus a. Okay, let's be really clear what that means. So what it's saying, let's say we've got some curve that looks like this, and here's a, and here's b over here, and the area that I just drew, that is the integral from a to b of f of x dx. And what we were saying before is that there's some, some average value of that function. And the average value, this is our average value. So what it's saying is there must be some, maybe it's like right here, probably a little bit lower, but that's close enough. So this here is my average value, and we call it f of c, which, and what we're saying here is that there must be some c value, so like at least one, and maybe more, and in this case more, such that, so there exists c such that f of c equals, and I'm just going to rewrite this slightly different, such that f of c is the average value of my function over that interval. So in other words, this is saying that there must be an average value of a function provided that it's continuous, and not only is there an average value of this function, but there's an x value c that's in between a and b such that f of c is the average value. So let's see this problem in action. It says find the average value of the function on the interval from 0 to 2. So let's, first of all, what does this graph look like? That's 1, 2, looks something like this. So what we want to do is we want to find f of c such that it equals the integral, of x squared minus 2x plus 1 dx from 0 to 2. Okay, well, what do? We take the antiderivative of that. We get 1/3 x cubed minus x squared plus 1 integrated from, plus x integrated from 0 to 2. And this equals 8/3 minus 4 plus 2, which is 8/3 minus 2, which is 6/3, which equals 2/3. Okay, so then that's what this definite integral equals. So now we need, and that's just the definite integral. So the average value, and I forgot to do this, this should be divided by 2 minus 0. So divided by 2 minus 0, divided by 2 minus 0, because remember, we're dividing by the b minus a. So this ends up equaling 1/3. And so what that's saying is that there must be some value c such that f of c equals 1/3. So we say, okay, well, to find that value c, we're going to let 1/3 equal x squared minus 2x plus 1 and see where that happens. Well, you know, on our graph, that's happening right there and there. And let's just see what that looks like. So we're going to graph y equals 1/3 and y equals, and if you have a Inspire calculator, you can just use the solve button for this, but for us still using the 83s and 84s, graphing I think is the easiest method. So we're going to see where it intersects. And I forgot to add a squared. So then we just find where it intersects. So second calc intersect. So the first intersection is at 0.42. Interesting marker choice. And I'll find the other one. I'll pause the video and do that. So our second one is at 1.58. So what is the significance of this? So these are, I say x, maybe I should, instead of putting x, I should have put c. These are my c values such that, you know, when I put these values into my function, it gives me the average value of that function over the interval from 2 to 0. All right, so we're going to finish off with two challenging problems. Try what I suggest that you do is pause the video, see how much of this you can do on your own, then unpause the video and watch the solution. So we've got a region shaded by 4 minus x squared and 1 plus 2 sine x in the first quadrant. So it says find the area of R. Well, the first thing that we need to do is find that intersection. So I'm going to use my calculator to find that intersection. So it intersects at 1.1. That's important for us because that's going to be one of our limits. So let's put in 1.1. And it says find the volume of the solid, find the area. So we haven't found that yet. So we're going to integrate from 0 to 1, top minus bottom. So 4 minus x squared minus 1 plus 2 sine x dx. Well, we can get rid of that. We can distribute that negative, so that's just, let's put an eraser here. That's just minus and minus. So taking the antiderivative, we get 4x minus x cubed over 3 minus x plus 2 cos of x. Evaluate that from 0 to 1. And then we just plug in. So we have 3x, or sorry, 3, because I'm putting 1 in. So we have 3 minus a third, putting 1 in, plus 2 cos of 1, minus, and then when I put 0 in, these will all be zeros, but cos of 0 is 1, so minus 2. So simplifying that, I have 2/3 plus 2 cos of 1. And that would be the exact area. What about the volume of the solid generated when it's rotated around the x-axis? Well, okay, we've done these problems before. So here's the radius of my top disk. And again, that's going to rotate around the x-axis and create a disk with a little bit of depth, dx, with a radius of that. So we're going to integrate again from 0 to 1.1. I just realized that in the last video, or in this slide, this should have been 1.1, which would change these numbers a little bit. So given that it's just algebra at this point, I'll just leave it like that. So this is our expression for the area. And then you could plug in those numbers and get it. We don't need to do that now. Okay, so here we have 1.1, and we want to do, the equation is pi r squared. So we can put a pi out here, and r squared is 4 minus x squared. And then I want to subtract away this radius, which is, and this should be squared, and that is 1 plus 2 sine of x squared dx. And for a problem like this, we could evaluate by hand, or really that would be pretty tricky. So this you can expect to use your calculator. So you could just put this into your y1 and integrate it to get a value. But the hard part is just setting up the integral. And then the last one, what's the volume of the solid whose base is r and whose cross-section is perpendicular to the x-axis? So in that idea, this, if we were to take out this sliver and pull it out, what that would have is a rectangle, sorry, a square with little depth dx, and the height, well, this height would be 4 minus x squared minus 1 plus 2 sine of x. So the area would be that squared. So the expression for our volume would be the integral from 0 to 1.1 of our sides, 4 minus x squared minus 1 plus 2 sine x. And then we square that whole thing, because it's squared because it's this side times this side, and it's a square, so it's squared, times its little depth, dx. And this is an expression for C. And we don't need to actually evaluate these expressions. If you really want to know what the answer is, the answers are down here. Let's go and do this last. Okay, this is a really terrific problem because it requires us to A, have a good understanding of graphics, and B, use some application of calculus. So we have this function, this parabola, y squared equals 6x. Now that's going to look something like this. Hopefully you remember studying conics in pre-cal. Well, this is a parabola that's symmetric around the x-axis. And then we have this this line y equals 3x plus c, where c is some constant. And the first question says, determine all values of c for which the graphs intersect in two distinct points. Well, what we can see is, what we can see, SEE, is that provided, anytime our line, there we're going to hit in 2 points, and here we're going to hit in 2 points. So anywhere, kind of down here, we're going to be hitting in 2 points. And up here, we don't hit at all. So what am I doing with these lines? Let's just be clear. This is the family of lines y equals 3x plus c, where c is my y-intercept, and so I'm just changing the value of c. So if we want to find all values of c for which the graphs intersect in two distinct points, we need to find the place where all of a sudden they start intersecting at 2 points. Well, that's going to happen when, right at this special place here, there's going to be one point. There's going to be one point here where my line is tangent. And where it's tangent, it's going to hit only once. And, I need to find out what is that c value here, because as long as, and we'll call this c naught, because as long as c is less than c naught, meaning as long as c is below this line, we're going to intersect in two places. All right, so how do we do that? Well, we need to find where the line is tangent. This is an interesting problem. So where it's tangent is going to be where this parabola has the same slope as this. So we know that everywhere here, y prime equals 3. It's a linear equation where the slope equals 3. We know that. So now let's find the derivative of this equation. So we have 2y dy dx equals 6. And if we solve that, we get, we'll write that as y prime equals 3 over y. And what we're looking for is the place where my derivative, I want to know, when is my derivative equal 3? Because when they're tangent, this curve, y squared equals 6x, this curve and this line need to have the same slope, because that's when they're going to hit only once. So these need to equal each other. So we're going to say 3 equals 3 over y. So therefore y equals 1. Well, when y equals 1, what is my x value? Well, when y equals 1, we have 1 squared equals 6x. So x equals 1/6. And that's just plugging that into this equation here. So therefore, to find c, to find our c value, we know, going to my equation, y equals 3x plus c. At the point where they intersect once, where they have the same slope, where they're tangent, that's going to be at the point 1/6, 1. So I'm going to plug those points in. 1 equals 3 times 1/6 plus c, and we get that c equals 1/2. That's this value, 1/2. So the values for which the graph intersects in two distinct points are going to be all values of c that are less than 1/2. In the next question, it says, let's suppose that c is -3/2. Find the area of the region enclosed by the two curves. So we've got this, and we've got this line here. So the key to this problem is for us to say, let's consider, let's split up these two graphs into my blue graph and green graph, where the green is y equals negative root 6. Sorry. Yeah, root 6x. I'm just solving this equation. I'm square rooting both sides. And we get a plus or minus. And here's the minus version. And up here, this is y equals root 6x. And then I've got my line y equals 3x minus 3 halves. So to find this area, I'm going to need to split it up into two sections. You know, I need to find this intersection and this intersection. So let me do that first on the calculator. Okay, so this occurs, our first intersection point is at 1/6, and this intersection point is at 3 halves. These are the x values. And the key reason why we needed to find those two values is, and I'm going to draw this picture just a little bit bigger to make it more clear. The upper value, the upper function stays the same throughout, but the lower function changes. So in that first, in these first strips, the height of that is going to be root 6x minus root 6x versus my later strip, and a strip here, the height of that strip is root 6x minus 3x minus 3 halves. So to find the total area, what we're going to do is we're going to integrate from 0 to 1/6 the height times dx. So this ends up being plus, so we get 2 root 6 x dx, and that's going to find this area right there. And then the area afterwards is where our lower function switches to this line. So then we're going to add from 1/6 to 3 halves the upper minus lower, which is root 6x minus 3x minus 3 halves. And this is integration that you can do on your calculator, or you really can do by hand, but I don't think you want to spend some time doing that right now. The key part is, find the intersection points and then set up the two different sorry about that. We need to set up the two different integrals with the two different height equations. So here's the height of the first rectangle, and here's the height of my second rectangle. And again, we needed to do that because the lower function switches there. All right, so let's answer the last question. In the last question, it says, now suppose C equals 0. Find the volume of the solid formed when the region bounded by y equals 3x and y squared equals 6x is revolved around the x-axis. Okay, so we find out the points of our intersection, and so that's happening here. They start at 0, and this is the point 0, and this is the point 2/3, and we're going to take this whole region and revolve it around the x-axis. So we're going to take this region and revolve it around the x-axis. Well, just to blow that region up so that we can see it more clearly, we are going to think of this as, cutting a vertical strip. And again, really need to know this idea. You're cutting a vertical strip, and then we're going to rotate that disk around, and that's going to get us a disk that looks like this. A little bit of depth, dx. And then we're going to subtract away that empty volume, which is going to be inside. And we get, a nice looking donut, which we can't eat because it's on the computer screen, but, imagine that's the shape that we're going to get. And so we know how to integrate that. We're going to use our equation, the integral from 0 to 2/3 of our top function, which is root 6x squared minus our bottom function, which is 3x squared dx. And that's with a pi in front. And remember, this is just pi r squared. That's the equation for a circle times the dx, and that gives us the little bit of a cylinder. And just in case you're curious, there's other solutions to these problems with numerical answers here and here. Okay, thanks for watching.